we discussed about the Riemann sum and the definite integral. So let's start with a function f that is continuous on the interval AB. We divide the interval AB into n subintervals, not necessarily of same length, not necessarily equal. Okay, so let us call this as partition delta. Call this as partition delta. So our partition delta is x sub O equal to A, x sub 1, x sub 2, x sub I minus 1, x sub I, x sub n. So let us illustrate this. X sub O equal to A, x sub 1, x sub 2, x sub 3, say x sub I minus 1, x sub I, x sub n minus 1, x sub n. So our delta 1x is the length of the first subinterval xo to x1 or x sub 1 minus xo. Delta sub 2x will be x sub 2 minus x sub 1. So delta sub ix will be x sub I minus x sub I minus 1. Next, we're going to choose a point in each subinterval. Let us call that point as C. So for the first subinterval, let us call that as C sub 1. Second subinterval, say it is close to the right endpoint, call it as C sub 2. On the third subinterval, let us say that that is the right endpoint, C sub 3. We continue on our selection of points inside the interval. Say for the ith subinterval, that is C sub I. Okay. So this is the ith subinterval. And the width is delta sub ix. And we do that for all the other subintervals. So that is our C sub n. Next, we form the sum. We form the sum R. Form the sum R as follows. Okay. So R is equal to f sub C sub 1 delta sub 1x plus f of C sub 2 delta 2x plus and so on and so forth f of C sub n delta sub nx. In a more compact form, we write this as the summation of f of C sub I delta sub ix I from 1 to n. Now this sum, this is called a Riemann sum of f on the interval AB using the partition delta. Okay, so the expression is a generalization of the sum we have seen regarding the area of a plane region. Remember, we solve for the area of region R using the limit of the sum of f of mi delta x I from 1 to n as n increases without bound. This sum of f of mi delta x I from 1 to n is an example of a Riemann sum using the partition delta, and the type of partitioning here is a regular partitioning. Regular in the sense that your delta x is equal. No? The width delta x is constant. For the Riemann sum, it is a generalization. The length delta x is not necessarily equal for all the intervals. Okay? So we can think of the Riemann sum as the generalization of the sum part, the summation part of the definition of the area of a plane region. So let us have an example. But before that, before the example, one further illustration of the Riemann sum is related also to area. So here's the interval from A to B. Then we made the partitioning x1, x2, say x3, x sub I minus 1, x sub I, x sub n minus 1, and x sub n equal to b. Or x sub n equal to b. There. Then we chose a point in each subinterval, c sub 1, c sub 2, c sub 3, then c sub I minus 2, or no, that is c sub I minus 1, then c sub I, then c sub I plus 1, c sub n. And supposing that this is the function y equal to f of x. If we multiply our delta x sub 1, which is this much, this much, okay? If we multiply this delta x sub 1 with the height f of c sub 1, this is my f sub c sub 1. That will give me the area delta sub 1a, the area of that rectangle. And we'll be doing that for all the subintervals using the specified height or using the specified point, no? Because that point will determine the height of the rectangle. And we do that for all. So in this case, this will be the height based on the chosen point. Based on the chosen point. Okay. So the Riemann sum geometrically represents the sum of the areas of the n rectangles. neither inscribed nor circumscribed, no? Because it depends upon the point chosen. So the Riemann sum is the sum of f of c sub I delta ix, I from 1 to n, and it approximates again the area of the region beneath the graph of y equal to f of x. So this is a generalization of our summation of delta A, which is the sum of f of mi delta x, I from 1 to n. So this is also a Riemann sum. But it uses general partitioning because delta x is constant from one interval to another. Okay? So let us have an example. Let us say that the function is f of x equal to x squared plus 2x minus 1, and the interval is 0 to 2. We are given the partition delta. Okay, say x sub o is 0, x sub 1 is, let us say, 0.3, x sub 2 is 0.6, x sub 3 is 0.9, x sub 4 is 1.1, x sub 5 is 1.3, x sub 6 is 1.5, x sub 7 is, let us say, 1.9, and x sub 8 is 2. Right? Then we have the set of points, C sub I. C sub 1 is 0.2, no, between 0 and 0.3, inclusive of the endpoint. So C sub 2 is, say, 0.5. C sub 3 is 0.8. C sub 4 is, say, 1. C sub 5 is 1.2. C sub 6 is 1.5. C sub 7 is 1.8. And C sub 8 is 2. Now, based on this partition delta and set of points C sub I, find the Riemann sum R. Okay. So we need to find first the width of each subinterval. So we start with delta sub 1x, which is x1 minus xo. That will be 0.3 minus 0, which is 0.3. Delta sub 2x, that will be x2 minus x1. 0.6 minus 0.3 is 0.3. Delta sub 3x, that is 0.9 minus 0.6 is 0.3 also. Delta sub 4x, that is 1.1 minus 0.9, 0.2. Delta sub 5x, 1.3 minus 1.1 is 0.2. Delta sub 6x is 1.5 minus 1.3 is 0.2. Delta sub 7x is 1.8 minus 1.5, 0.3. And delta sub 8x is 2 minus 1.8, 0.2. Okay, as you can see, our delta x is not a constant value. No? The delta x's are 0.2 and 0.3. Next, we have to solve for f of c sub 1 or f of 0.2. The point chosen in the first subinterval is 0.2. Remember, our f of x is x squared plus 2x minus 1. So you simply substitute 0.2 to x. So that will be 0.2 squared plus 2 times 0.2 minus 1. That will be 0.04 plus 0.4 minus 1. So 0.44 minus 1 is negative 0.56. Okay, so let us check that. 0.2 squared is 0.4, 2 times 0.02, 0.2 is 0.4, minus 1, 0.44 minus 1 is negative 0.56. Next, our f of c sub 2, that is f of 0.5. So 0.5 squared plus 2 times 0.5 minus 1, that will give you 0.25 plus 1 minus 1. F of C sub 3. C sub 3 is 0.8. So F of 0.8 is 0.8 squared. 0.8 squared plus 2 times 0.8 minus 1. That will be 1.6. 0.6 plus 0.64. 1.6 minus 1 is 0.6 plus 0.64, 1.24. F of C sub 4, that is f of 1. So 1 squared plus 2 times 1 minus 1, that will give me 2. F of C sub 5, our C sub 5 is 1.2. So 1.2 squared plus 2 times 1.2 minus 1. How much is that? 1.44 plus 2.4 minus 1 is 3.84. Okay? Wait. 2.84. 2.84. Again, 1.2 is 1.44. 2 times 1.2 is 2.4. Adding them up, 3.84 minus 1 is 2.84. Okay, so we continue. F of C sub 6. Our C sub 6 is 1.5. So F of 1.5, 1.5 squared plus 2 times 1.5 minus 1. 1.5 squared is 225 plus 3 minus 1. So 5.25 minus 1 is 4.25. F of C sub 7 is f of 1.8. So 1.8 squared plus 2 times 1.8 minus 1. What is 1.8 squared? 1.8 times 1.8. That will be 64, 144, 18, 412, 3.24. Again, 8 times 8, 64. Carry 6, 8, 14, 18, 4, 12, 3.24. Plus 2 times 1.8 is 3.6. So that will be 6.84 minus 1. 6.84 minus 1. Let me check. That is 3.6. 6, so 5.84. Finally, f of C sub 8. F of C sub 8. That will be f of, our C sub 8 is 2. So f of 2 is 2 squared plus 2 times 2 minus 1. So that will be 2 squared 4 plus 4 is 8 minus 1, 7. So those are the computation for f of C sub I. The next thing that we will do is we'll just get the Riemann sum by multiplying f of C sub I by delta sub ix and then adding them up together. So let us do just that. So the Riemann sum is equal to the summation of f of C sub I delta ix I from 1 to 8. That will be 0.56 times 0.3 plus 0.25. By the way, this is negative 0.56. Okay? Negative 0.56 times 0.3 plus 0.25 times 0.3 plus 1.24 times 0.3 plus 2 times 0.2 plus 284 times 0.2 plus 4.25 times 0.2 plus 5.84 times 0.3 plus 7 times 0.2. And you do some calculation here. You can use your calculator and you will get the sum. And that is the Riemann sum corresponding to the given partition delta as well as the set of point psi sub I. Now, geometrically, these are approximates the area. No? But since it's just the Riemann sum, it has no unit. No? The Riemann sum has no unit. But you can use this value to approximate the area of the region, no? Under the graph of F. So if you are asked find the approximate area of that region R, you can use this Riemann sum and then affix the unit. Say square units, square meter, or square centimeter, whatever unit is given, no, for the measurement. Okay? So the value of the Riemann sum for that function will depend on two things. The manner by which the interval is partitioned. So there are infinitely many ways of partitioning the interval. You can have regular partitioning. That's one. You can have a partitioning wherein for the first partition, you have delta x. For the second partition, it will be twice delta x. Then 3 times delta x. That's another partitioning. And also, the points chosen in each subinterval. You can either use all the right endpoints. You can use all the right endpoints as your C. C sub 1, C sub 2. Or the left endpoint, or the midpoint, or any of the trisecting points. So, again, the Riemann sum will depend on the partition, on the interval, and the set of point C sub I. Alright? So we are now ready to define the definite integral. So let f be a function continuous on the closed interval AB. The definite integral of f from A to B, denoted by the long elongated s fx dx from A to B, is defined by f of x dx from A to B as the limit of the Riemann sum, or the sum of f of c sub I delta sub ix I from 1 to n as the norm of the partition approaches 0. Okay, so we have a new symbol here. This symbol, it is called the norm of the partition. Okay. So this is the norm of the partition. It is defined to be the longest subinterval. The longest subinterval. So if this is the manner by which the interval was subdivided, then this will be the norm of the partition. No? So the norm of the partition approaches 0. Meaning to say, no, that the length of the longest subinterval is made to decrease, no, approaching 0. And this is equivalent to the number of subintervals increasing without bound. So the norm of the partition is nothing new after all, no? Because it is the same as n increasing without bound. So now we know that the definite integral is simply the limit of the Riemann sum. Okay? And how do we get the limit of the Riemann sum? By finding first the sum of f of c sub I delta sub I x. And to do that, you have to define the partition. Of course, you can use normal partitioning or regular partitioning. It will simplify everything if you will use regular partitioning. And regular partitioning is that delta x is constant, which is simply equal to b minus a all over n. That is the simplest partitioning. All right, that is the simplest partitioning delta. The regular partitioning b minus a all over n, wherein delta x is constant. And then for your f of c sub I, it's important that you define your c sub I. You can use any point, no, in the interval, but it will be easier if you will use, say, all the right endpoints as your c sub I. C sub 1, C sub 2, C sub 3. Or you can use all the left endpoint. You can use the left endpoint. C sub 1, C sub 2, C sub 3, and C sub 4. Just for us to simplify, no, the Riemann sum. We use regular partitioning, and in choosing the point C sub I, we choose the same location or yes, same location for each subinterval. Let us be consistent in our selection of C sub I. Either we choose all the midpoints, we can do that. Choose all the midpoints of all the subintervals. That is a good selection for C sub I. Then you get the value of f of C sub I, get the sum of the product, and eventually evaluate the limit. And this is nothing new to us, no? Because we have already done this in finding the area of a region. Limit of the sum of f of mi delta x. We have already done this before. So to find the definite integral is to find the area of the region beneath the graph of f of x. So if you want to find the definite integral of f of x dx, you simply get the area of the region beneath the graph of f and between the vertical lines x equal to a and x equal to b above the x-axis. All right, so let us have an example. You evaluate the definite integral of 4x plus 1 dx from 1 to 2. Okay, so it says that the function from the given integrand, the function f is defined by f of x equal to 4x plus 1. Your lower limit is 1 and your upper limit is 2. Okay? So the definition of the integral, definite integral of fx dx from a to b is the integral of 4x plus 1 dx from 1 to 2 equal to the limit of the Riemann sum f of c sub I delta sub I x I from 1 to n as n increases without bound. Okay, so you can also write this as 4c sub I plus 1 because that is your f of x. Replace x by c sub I and delta sub I x. Okay, so let us have this as our workspace. Our f of x is 4x plus 1. So let us use delta ix equal to delta x, regular partitioning, b minus a all over n. So that will be 2 minus 1 over n or 1 over n. Okay, next, we choose our c sub I as x sub I, meaning to say This is x sub I minus 1, x sub I, this being our ith subinterval. And let us choose our c sub I to be the right endpoint of the subinterval. Okay? So, our f of c sub I is 4c sub I plus 1. Okay? Here, you replace x by c sub I. So that will be 4c sub I plus 1. But we have to express our c sub I in terms of delta x. Okay? Since our lower limit is 1, x sub I will be 1 plus I delta x. No? Remember, if this is 0 and this is a, this is your x sub I. From a to x sub I, that is I delta x. But we have to add this much, which is a. So in this example, a is equal to 1. So from 0 to x sub I, that will be equal to 1 plus I delta x. That is my c sub I. Alright? So, that will be equal to 4 times xi, or c sub I is 1 plus I delta x plus, okay, 1. That is my f of c sub I. F of x is 4x plus 1, so f of c sub I is 4c sub I plus 1. But your c sub I is 1 plus I delta x. So that is equivalent to 4 plus 1 or 5 plus 4I delta x. Alright? So we continue. That will be the limit of the sum of 5 plus 4I delta x times delta x. By the way, let us work on the sum separately. I from 1 to n as the norm approaches 0. So let me segregate the sum part. Sum of 5 plus 4 I delta x times delta x, which is equivalent to the sum of 5 delta x plus 4I delta x squared. Okay? But our delta x is what? Our delta x is 1 over n. 1 over n. So plus 4 sum of I delta x is 1 over n squared. Okay? Sum of 5 delta x plus sum of 4I delta x squared. So this is equivalent to what? 1 over n times the sum of 5 plus 4 over n squared sum of I. Okay? And the sum of the constant 5 is 5n plus 4 over n squared. The sum of I, the formula is n times n plus 1 all over 2. Okay? So, 1 over n times 5 over n, that will be 5 plus 4 over 2 is 2. This will be n squared plus n. So, 4 divided by 2, that will be 2. So, 2n squared plus 2n all over n squared. That will be 2 plus 2 over n. Or equivalently, 7 plus 2 over n. So, that is the sum. Continuing here, that will be the limit of the sum. 7 plus 2 over n as the norm approaches 0. So it's similar to, as I have said earlier, this is the same as n increasing without bond, no? For regular partitioning. So this one will approach 0. So the answer, our final answer then would be limit of 7 is 7. And there will be no unit. No unit. Why? Because we are talking about the definite integral. But if you are asked what is the area of the region below the graph of 4x plus 1 between 1 and 2, then the result here will be expressed in the appropriate square units, 7 square units. But since we are asked to find the definite integral, our answer will have no unit. It is dimensionless. Okay? So in here, what set of points C sub I did we use? We used the right endpoint. No? You can try by using the left endpoint, by using x sub I minus 1. So you can solve the following exercises. You can evaluate the integral of 3 minus x squared dx from 0 to 1. The integral of 5 plus 3x minus x squared dx from 2 to 3. So you can choose any c sub I. Any c sub I. Okay?